we go. It's back. The recording thing is up.
It is? Okay.
I can see it.
When you look at the screen on Zoom on the top left, there's like a little check and it's green. And then to the right of that, there's a recording thing that pops up when it's recording.
Okay. Thank you. Now, can you see my screen?
I can't see you sharing anything on your screen now.
No.
I'm technologically challenged. Sorry.
It's okay. It happens to the best of us.
And I'm not the best.
Typically breaks for reasons unknown until it fixes itself.
At home, I always have to have my kids help me out. Be able to see stuff now, I think.
Yes, we can see your tablet again.
And it says recording in the top left, so we're all good.
I can see the screen.
Yep.
Yep.
You got it all down.
All right, let's move on. All right, so as I was saying, in the days prior to quantum mechanics, people thought that the electrons were like tiny particles which move in straight lines between the nuclei. And you think of that as empty space, but every now and then they bump into one of these atoms and change the direction, okay? But once quantum mechanics was developed, people realized that that wasn't the correct picture because then the average distance electrons would travel between collisions should have been comparable to the lattice constant, which is a very, very small number. It's of the order of angstroms. Well, experimentally, it was clear the electrons seem to be able to propagate much longer distances, maybe thousands of lattice constants. So there's something funny about the classical picture. Okay? So once the quantum mechanical picture was developed, people realized that electrons also, in addition to having a particle type character, they also have this wave type character, these de Broglie waves. And once you launch a de Broglie wave in this periodic arrangement of atoms, the wave will propagate forever without undergoing any additional collisions because the interactions with the periodic arrangements are captured by this concept of effective mass. All right. So then, of course, the question arises, what causes collisions or scattering in a crystal? The collisions or scattering in a crystal are not caused by the periodic arrangement of the atoms, but anything that is deviation from perfect periodicity. So that's what's shown in the middle. So these are the forces due to scattering or collisions, okay? Scattering or collisions, okay? So any potential V, which is a function of position R and time T, which is random, which is not this perfectly periodic crystalline potential, is what causes scattering. So I want this to sink in, okay? It's a very, very important concept, okay? So what I'm saying is if you launch an electron in a perfectly periodic potential, as you see in a perfect crystal, you will not encounter any collisions or scattering of the electrons with the perfectly periodic atoms. Instead, you have to think of this electron now as a wave, which kind of surfs effortlessly through this perfectly periodic arrangement of atoms. And all that the periodic forces of the crystal will do is change the actual electron mass m0 into a new modified mass m star. And that's what comes out of the solution of the Schrodinger equation. Once you use the effective mass, you should ignore the periodic crystalline forces anymore because that will be sort of double counting the impact of the periodic crystalline forces, okay? So now these particles with an effective mass can only undergo scattering if there are any deviations from this perfectly periodic crystalline potential. And that, of course, is a huge conceptual leap, okay? So let's do some thought experiments and see if we can figure it out, okay? So if I have a crystal with a lattice spacing as shown on the left-hand side versus another crystal where the same atoms are kept very close together, okay, that's crystal 1, crystal 2, identical atoms, but in case 2, the atoms are more closely spaced together. In which crystal would the electrons have a tougher time traveling? 1 or 2? That's a
The
trick
1.
question.
I would assume 1. Wouldn't they fall deeper into the dip?
Okay, assuming they have, so maybe I'm, it's probably a tricky question, okay? In which crystal, 1 or 2, would the electrons undergo more scattering? Let me rephrase that.
2, because they're like,
Yeah.
No, so that's a conceptual difference between classical physics and quantum mechanics, okay? So if both of these are perfectly periodic, there will be no scattering in either case, okay? All that might happen is they would have different effective masses, but there will be no collisions or scattering in either case. If both of these are perfectly periodic crystals, okay? And things get even funnier. So now let's look at crystal 1, which is perfectly periodic, okay? And I'm saying that when I launch electron, you shouldn't think of this as these particles which bump into these atoms, but rather as a wave, which once I launch into the periodic crystal, it will travel forever without any scattering or collisions, okay? But now let me change the problem statement and maybe remove a couple of these atoms. So maybe I remove this atom, that atom, okay? So that's case 2, say. Case 1 is I haven't removed any of the atoms. It's a perfectly periodic arrangement of atoms. And case 1 prime is when I've removed a few of the atoms and created vacancies. In which case do you think there would be more scattering? Case 1 or case 1 prime, where I've removed a few of the atoms?
1 prime?
Very good.
Yeah.
So that you've got it now, okay? So you'd think from classical physics that if I've removed a few of the atoms, there's more empty space, right? And surely the electrons would be able to travel more easily. But empty space, if I create random empty spots, empty vacancies, that's a deviation from perfect periodicity. And once again, that is what causes scattering, okay? So it's a very, when you first think about it, at least as electrical engineers, we tend to think of electrons as these, tiny charged particles with a negative charge. I mean, that's true to some extent, but a deeper picture is this wave picture, okay? Now, this classical picture is a nice sort of crutch, mental crutch, if you will, okay? The only difference is when you think of this electron as a particle with a negative charge, this bumping into things is not bumping into the periodic atoms themselves, but bumping into defects such as this, random potential. So as long as you think of these electrons as particles bumping into these defects, the Drude picture is a nice picture. And people still use that with the difference that it's not going to bump into the periodic arrangement of the atoms, it's going to bump into variations from perfect periodicity, okay? So that's what we're going to determine the sort of mean free path between collisions, all right?
Is it the field, like differences in the field that's bumping into? Quote
Yes,
unquote?
you can think of it that way. Okay, you can think of
Okay.
this field as a time and space dependent random field, electric field. Okay, while the periodic forces also have an impact on the electron, but that impact is captured by this effective mass. So I'm not ignoring the periodic forces. It's just that I'm capturing that as an effective mass, and since it's perfectly periodic, those block type wave functions can propagate forever without colliding with the periodic atoms themselves. All right. So once I have that effective mass, the only time I'll have collisions or scattering is any deviations from periodicity. Okay. Now let's go back to the final one, which is the main topic today, which is external forces. Okay. Now, if I didn't have any external electric fields, we saw that in the periodic crystalline potential, we get bands where you have conduction band, valence bands, which are flat, right? Because remember, the band minimum corresponds to just potential energy. And as you go up, you add electron kinetic energy. As you go down, you add hole kinetic energy. That's electron kinetic energy. But if I have flat bands, that means that the electrostatic potential is constant. And since E equals minus dV dx, where V is electrostatic potential, that means in this case, electric field is equal to 0. What happens if I have a non-zero electric field? Well, EC and EV would vary with position, right? So in this particular case, we have electric field which points to the left, all right? And because Okay, let me ask you instead of giving me the answer. Now, in this particular case, EC and EV are shown by these dotted lines. Can you tell me just by looking at the figure, is electric field constant or itself a function of position?
It looks to be a function of position since it's not a straight line, right?
Very good, excellent. So at each point, you take the slopes minus dV dx, and you see that the slope here is different from this slope, right? So you have E, which is a function of position R or X. Excellent, okay? So we saw earlier on that if I look at electrons at this position, say R naught, okay? What is the kinetic energy of that electron?
0.
0, it's at rest. Does that electron see any force or does it not see any force?
Should be experiencing forces from the atoms, right? I'm assuming potential, but I'm not.
Well, the forces to the atoms are captured in terms of the effective mass, right?
Oh, okay.
But are there any other forces in this scenario? If I have electric field E at this location, electrons have a charge of minus Q. What is the force on the electron then? The external force.
If the field isn't changing, though, isn't there not a force being exerted on it? Like, doesn't it have to be moving through?
No. The force is given by charge times electric fields. So if electric field is 0, in flat bands, there are no external forces. But if force is charge times field, right? Electric field. Hello?
Yep.
So is the force 0 or non-zero?
Non-zero.
Non-zero. Okay, so in this particular case, the electric field points to the left, okay? And we'll see that in just a second. And therefore the force will be to the?
Should be to the right.
Very good.
Yes.
So it moves this way. So as it moves this way to say a new location R1, what is the kinetic energy? 0 or non-zero?
Moving, so non-zero.
Non-zero. How much kinetic energy do I have? That much kinetic energy, right?
Yeah.
How far above the band edge it is. Where did you get the kinetic energy from?
The external electric field.
Yeah.
You're very good. Okay. Similarly, if it's a hole over here, electric field to the left, holes move this way. Here, the whole kinetic energy is 0. Here, it's non-zero. It's got that much kinetic energy. Okay. And as it moves at different locations, the external force varies because, as you pointed out correctly, the slopes are different. So the electron of the hole sees different forces at different locations, the external forces. All right. The internal forces are also there, but that's been captured already in terms of this effective mass. Okay. And as it moves, every now and then, it'll bump into this random variation of the forces within the crystal due to defects or these atoms vibrating and things like that. All right. So this is a very important conceptual slide. Midterms are coming up. Oh, by the way, so all that you'll be tested on in the midterms is material covered up to the end of this lecture. Okay. So what we discuss on Monday next week will not be covered. Okay. And I have put in a question related to this slide. So study this very carefully and make sure that you understand the physics. All right. So now let's go back to the external force. That's our main topic today. I want to calculate what's called the current due to these external electric fields, which is known as drift current. All right. So now let's assume I have electric field pointing to the right. We'll see that the bands will vary at slope as shown over here. I'm assuming over here I have a constant electric field, and that's shown by a constant slope or a constant gradient of EC and EV. Okay. The electric field, we said, is given by minus dV dx, where V is electrostatic potential. Now the energy of the electron at the band minimum, EC, is given by then minus Q times this electrostatic potential. Okay. Therefore, you can rewrite this electric field minus dV dx as 1 over Q dEC dx. Okay. So the two minuses give you a net plus. So EC is equal to minus QV. So if I stick that in over here, minus dV dx is the same as plus 1 over q dEc dx. Now EC, EV, and the mid-gap potential EI, they're all, of course, parallel to each other, okay? Because EC minus EV is your band gap, which is a material constant, and EI, we saw the intrinsic Fermi level is sort of in the middle of the gap. So all of these are going to be parallel to each other. So you can write the electric field either as dEc dx, dEv dx, or dEi dx, okay? So what you find is if my electric field points to the right, the slope will be a positive slope. On the other hand, if the electric field points to the left, the bands would slope like this, all right? So once again, if I consider the electron, say over here, it's got 0 kinetic energy, it sees a force to the left, it moves, and it gains kinetic energy from the electric field. But then every now and then, it might bump into a defect somewhere over here, say, it may lose all or part of its energy, okay? Slows down. Then it moves, gains some kinetic energy. Maybe over here, there's another kind of defect, loses part of its energy. So these are the collisions that the electron encounters. It's not the electron bumping into the periodic arrangement of the atoms themselves. So where does this external electric field come from? Well, a classic example would be, you could take a slab of semiconductor of length L, width W, and thickness T. So the cross-sectional area A is W times T, okay? And to that, I apply a voltage, capital E. Don't confuse that with the electric field E that I showed in the previous class, okay? So what is the electric field E in this case? So electric field in this particular case, E shown with a Greek symbol, would be the voltage, capital E, divided by the length L, okay? So my electric field E is the voltage in the battery divided by the length of the device, right? And that electric field is what will cause the bands to slope like this. So what I'm interested in is calculating the current when I apply such a voltage to such a device, okay? Now, how do I do that? Now, when you apply this electric field, we saw that, let's consider holes, just to make our life simpler. So let's assume it's a p-type semiconductor. So the holes which have a positive charge would move in the direction of this electric field, right? And suppose in this, I have a hole concentration of p holes per unit volume. What I'm doing is I'm calculating this part of the current. Now, when I apply this electric field, the holes would move with an average velocity, which I call V holes. That's the drift velocity of the holes, which is going to be proportional to the electric field, okay? And the proportionality constant is known as the mobility of the holes. So it's proportional to the electric field, and it's given by the proportionality constant, the hole mobility, times electric field. And that's something that, hopefully makes sense from physical intuition, right? Because if I have a certain electric field, say 1 volt per centimeter, the holes will travel at a certain speed. If I double the electric field to say 2 volts per centimeter, it's reasonable that the velocity of the electrons will be twice as much. This, by the way, is what will lead to Ohm's law, where, of course, current is proportional to the voltage, okay? Now, if a particular hole travels at a velocity of VH, I want to calculate what the current is across a particular cross section over here, okay? So if this hole, which has a positive charge, moves across that cross section, any moving charge is, of course, what we call current, right? So the hole moving with the velocity V will carry a charge of plus Q. The charge times its velocity will give you the current into that single hole moving across this cross section. But of course, I don't have a single hole in the semiconductor. I have P holes per unit volume. Therefore, the current going across this cross section will be the hole velocity times the charge of the hole, which is plus Q, times the hole concentration per unit volume of P, okay? That gives you the current through a unit cross section. If I wanted the total current I, you have to multiply that by the cross-sectional area A, where A is the width times the thickness of the semiconductor. All right. The velocity we saw is proportional to the electric field, where the proportionality constant is the mobility. So you can write this as charge of the hole, which is plus Q, times mobility times electric field, which is the hole drift velocity. That's the current into a single hole per unit volume. But then if I have P holes per unit volume, you have to multiply by P. That gives you the current density due to the holes. This electric field over here is the voltage, capital E, divided by the length of the semiconductor bar. Okay, so then if I wanted, this gives you the current density, which is generally denoted as J. Okay, if I wanted the total current, you then have to multiply with the cross-sectional area, A, which in this case is W times T. And then looking at the hole contribution, that's Q, hole concentration per unit volume, hole times hole mobility, times electric field, which in this case is voltage divided by the length. Okay. Now notice this is nothing but Ohm's law because I see that the current I is proportional to the applied voltage, and everything else will give you the resist. It will be the 1 over the resistance term. Okay. So far I have looked at the contribution due to holes. How about the electrons? Well, electrons are a little bit harder to visualize in this context because they have a negative charge. Okay. So for electrons in the conduction band with a negative charge, which way are those electrons going to move in this case? The electric field is pointing to the right, right? The positive
Left
terminal.
them.
Very
It's
good.
opposite.
Excellent. So the electron moves in this direction. Okay. But if the electron moves to the left, which direction do you think that the current vector points for the electronic contribution?
Isn't it still in the direction the photons are moving, or the holes are moving?
Exactly. Because the electrons have a negative charge, although they are moving to the left, the current due to that points to the right, right? So when I come to the electron contribution, I get a electron drift velocity v electron, which is also going to be proportional to the electric field as long as Ohm's law is valid. The proportionality constant is called the hole mobility mu n for the negative carriers times electric field. The current due to that is given by minus Q, because the charge of the electron is minus Q, okay? But because the velocity points opposite to the electric field, that minus sign and the minus Q give you a net charge of plus Q, okay? So although the electrons and holes are moving in opposite directions, the current contributions add up in the same direction as the electric field, okay? So this then is the expression for the current density J, which is current per unit area, okay? And you have two components. You have the electronic component and the hole component as shown over here. This part can be combined as a parameter which is known as the conductivity of the semiconductor, which is the reciprocal of 1 over the resistivity of the semiconductor. So in 302 or in 411, hopefully you've seen the concept of resistivity rho of a solid, right? And once I write this as conductivity sigma or 1 over the resistivity, you'll start to see Ohm's law popping up. Okay, let's see how that works out. Okay, so I get current over area. So I is equal to now area times divided by rho, and then E over L, right? Voltage divided by the L, right? Now, do you remember the formula of the resistance of a rectangular bar?
I don't remember.
If I have a resistivity rho, the resistance of the bar is given by the resistivity rho, which is units of ohm centimeter, times the length of the bar divided by the cross-sectional area of the bar, A, which in this case is the width of the bar times the thickness of the bar, okay? So what I see over here is rho L over A is nothing but the resistance. So I equals the voltage divided by the resistance. And what is that called?
Ohm's law.
Very good. That's Ohm's law. Okay. So for at least low or modest electric fields where the velocities, the so-called drift velocities, are proportional to the electric field, you end up with Ohm's law. Now we'll see later on today, at high fields, Ohm's law breaks down because you no longer have a velocity which is going to be linearly proportional to the electric field. Okay. And if you think about it, this is a funny kind of a relationship which seems to violate Newton's second law. Because what is Newton's second law? Newton's second law is time rate of change of momentum, d dt of mass times velocity equals what? Force, right? And for the holes, for example, the force would be Q times electric field, right? So what Newton's second law would have predicted is if I apply electric field E, the holes should undergo a constant acceleration, right? Because d dt of mv, dv dt is acceleration. So that's nothing but mass times acceleration. If I have a constant electric field, I should have gotten a constant acceleration, right? The hole should keep speeding up. But instead, I'm claiming that in a solid, it's a velocity which is proportional to the electric field. So for a constant electric field, I end up with a constant velocity, right? So what's going on? What's going on is in a solid, remember the thing that we talked about collisions or scattering? Well, these holes or the electrons would accelerate in this external electric field, but then bump into some defect or scattering site, lose some of its energy. Accelerate in the field, bump into some defect or scattering site, okay? And on average, because of this periodic bumping events, not with the atoms themselves, but with deviations from periodicity. Hello?
Hi, is this Professor Banerjee?
Yeah.
My name is Christy and I'm with Bill Grant and Company.
I can't talk right now, sorry. I hate to ignore the phones because I'm always afraid that, my audio cut off or something and one of you are calling. Anyway, so as I was saying, if I apply electric field, Newton's law would have predicted that I would have a constant acceleration. The velocity would have kept up increasing linearly with time. But instead, because the electrons and the holes periodically undergo collisions or scattering, instead of a constant acceleration, you end up with a constant velocity, the so-called drift velocity, okay? So the analogous picture is, you can think of these electrons or holes moving in some sort of a viscous fluid, okay? And when a particle moves through a viscous fluid, for example, under gravity, after a while, it attains a steady state velocity. Instead of constantly accelerating under gravity, it'll reach a steady state velocity because of these frictional forces. So you can kind of think of these scattering events as the frictional forces of the electrons or the holes see. Okay. All right, so this is this expression for the resistivity, which is 1 over reciprocal of the conductivity. Okay. This is a very important expression. In the midterms, there's a good chance that I'll ask you to solve problems using expressions like this. All right. All right, so this next slide gives you a little bit more detail about the scattering events that I mentioned. So what I see, if I look at a cartoon view of a motion of a particle, electron or a hole in a solid, the electron or the hole travels in a straight line, but every now and then bumps into something, but that something is not the periodic atoms themselves. That something is some defect, time-dependent or position-dependent defect in the crystal, okay? It travels in a straight line until it bumps into some defect and so on and so forth, okay? Now, if I didn't apply any external electric fields, these electrons would bump into stuff and not go very far, okay? But of course, I don't have a single electron or a hole. I've got a whole bunch of them. So another electron or hole would do this and so on and so forth. So as a result, this whole ensemble of electrons would not have any net motion. So clearly, if I don't apply any external voltages, the net current across a cross section would be 0 because you'd have just as many electrons moving to the right as moving to the left. Okay, so they would all tend to cancel out on average. On the other hand, if I do apply electric field, say pointing to the right, and assuming I'm looking at holes over here, these holes do undergo this random motion because of bumping into defects. But in addition to that, because of the presence of this electric field, they'll do this. So it's undergoing collision, but over time, they have the net drift velocity of the holes to the right, okay? Another hole would have random motion, but then there'll be superimposed on top of that, there'll be a net hole velocity pointing to the right. For the electrons, of course, the velocity would be in the opposite direction, but because the electron charge is negative, the two negative signs would cancel, and the current contribution to the electrons also would be to the right in the same direction as the electric field over here. All right. And that then gives rise to this expression for the current density J, which we proved in the last slide is nothing but the current per unit cross section. Okay. Now this expression for the mobility, I'm not going to derive this, but I'll make this hopefully physically meaningful, is given by the charge of the electron. I'm looking at the electron mobility, same thing for the whole mobility, is given by the charge of the electron times the average time between collisions. Remember we said it collides with defects? Well, there's some average time between scattering events or collisions, which I call tau, divided by effective mass, but this is the conductivity effective mass. So this is the third effective mass that I told you last time we'll be talking about. The first effective mass that we talked about was in terms of the band curvatures. And if you look at the notes, you'll see that's given by h bar squared d2e dk square, right? That's the curvature of the bands. Now, in terms of those effective masses, we then saw that if I have different effective masses along x, y, z, when it comes to counting states, the density of states, you have to take the geometric mean to get the conductivity, to get the density of states effective mass. On the other hand, for the conductivity effective mass, because it appears as 1 over m star, and if I have three different effective masses, mx, my, mz, 1 over m conductivity will be 1/3 of 1 over mx plus 1 over my plus 1 over mz, okay? So you take averages depending on the way the mass term appears in your expression. So in the case of mobility or conductivity, since it appears in the denominator, that's the right way to do the averaging for the conductivity effective mass. Now let's see if this expression for mobility makes sense. If the average time between collisional events was very, very long, if it was able to travel for long distances before bumping into a defect, do you think the electrons or the holes would be able to be more agile? Would they be able to travel at faster speeds in electric field or slower speeds?
Can you repeat that question one more time?
If there were fewer collisional events, so that the time between collisions was very, very long, would you expect the electrons and holes to be able to travel more easily or less easily?
More easily because the numerator would be a higher value.
Right. The physical picture would be fewer collisions, would be sort of like less friction. Okay, so lower friction, the particles would be able to travel more easily. Okay. If the particles had a lower effective mass, they're lighter, obviously they'll be able to travel faster, right? So that's why mass appears in the denominator. And then Q, of course, is a constant. It's electron or the hole charge. Minus Q for electrons and plus Q for the holes. Okay. Now, in this case, we just take the magnitude of the charge. So mobility is a positive quantity, both for electrons and holes. All right. Now, in practice, in a semiconductor, you can have different types of collisions or scattering events. We'll talk about two of the most important ones next. So then, suppose I have a scattering event due to mechanism 1, scattering event due to mechanism 2. You write down what's called a scattering rate from an initial wave vector or velocity k to a final wave vector k prime. So what that means is you draw this velocity vector, say v1, and call that h bar k1 over m star, going to another velocity vector v2 corresponding to another wave vector k2. Okay, sorry, k prime, v prime going to k prime. Okay, so the way you write down this scattering rates is going from an initial wave vector or quantum state K into final state K prime, okay? If we now have multiple scattering mechanisms, S1, 2, 3, etc., the total scattering rate presumably would be the sum total of the individual scattering rates, right? The scattering rates are written as 1 over scattering time. So if you have multiple scattering mechanisms, you can write 1 over overall scattering rate over scattering time as 1 over tau 1 plus 1 over tau 2, and so on and so forth, okay? And since tau appears in the numerator for mobility, what you can do is you can take the reciprocal of the mobility, 1 over mu, that's proportional to 1 over tau. So then you can add the individual contributions to the mobility from a scattering mechanism 1, scattering mechanism 2, to get the overall scattering rate or the overall mobility. So the point is, in a semiconductor, if you somehow measure the scattering, the mobility due to scattering mechanism 1, and in a separate sample, measure the mobility due to a scattering mechanism 2, and then you have a semiconductor where both those scattering mechanisms are applicable, the overall mobility is given by an expression like this, which is known as the Mathiassen's rule. So if you have multiple scattering mechanisms, the way you combine mobility is by this rule, okay? Now, final picture over here is when I apply this electric field, as I mentioned, on top of this random velocity, you're superimposing this drift velocity, VH or V electron, in the opposite direction, okay? And that's shown by these velocity vectors. And that is the term which gives rise to the current, because now if I consider a cross section like this, it's this well-directed velocity component which is responsible for the current or the current density. The random components, they tend to cancel out because they're moving in random directions and you got a whole bunch of electrons or holes in the system. Now, what ends up happening, and this is not something that you'll be tested on in the class, is if after time t, you get rid of the electric field, what you'll find is because of these collisional events, pretty rapidly, these well-directed velocity vectors will get randomized again because of collisions, okay? And that characteristic time is known as the momentum relaxation time, all right? But for a small few nanoseconds or picoseconds, you'll see that the magnitude of these vectors are still pretty long, meaning that the kinetic energy, half mv squared, is still very, very high. And these electrons or holes are now called hot electrons or hot holes, meaning highly energetic electrons or holes. It takes another characteristic time constant, which is known as the energy relaxation time, for them to cool down to the ambient temperature, okay? Where the kinetic energy is now going to correspond to the room temperature of the system. So you'll get half mv squared equal to kT, where K is the Boltzmann constant and T is temperature in Kelvin. We'll discuss this more after spring break when we talk about excess carriers in a semiconductor. Okay, so that characteristic temperature at room temperature I mentioned a couple of times is 25 MeV. All right, so that velocity corresponding to ambient room temperature of 25 MeV is going to be smaller, but then if I apply the electric field, initially the electrons or holes will be at a higher temperature. That's why they're called hot electrons or holes. Everybody with me?
Yeah.
Okay. The most important thing from the point of view of exams is this expression, because I will expect you to calculate currents, these so-called drift currents in electric field. All right. Quickly, let's discuss the two mechanisms, the two most important mechanisms, collisional or scattering mechanisms, which determine mobility. The first of those is ionized impurity scattering. And this is unavoidable because we've seen in a semiconductor, to make a device, you always have to dope the crystal to introduce carriers, right? We saw that you have to introduce, for example, donor type impurities, such as phosphorus or arsenic, and that gives off that fifth electron. And this, of course, is in the silicon crystal. So that's my donor impurity over there, okay? And this electron then moves around. Now, this electron, when it moves in this crystal, which has been doped with the donor impurity, do you think it's going to see the donor type impurity as a defect, or is it part of the perfectly periodic crystalline potential, which does not cause any scattering? So I've replaced the silicon atoms. I'm indicating the silicon atoms by these open circles with a donor type impurity, maybe a phosphorus atom or an arsenic atom, say, okay, on the Bravais lattice side. Does that constitute a defect, or is it still a defect-free crystal?
Are you adding a new one or are you replacing them?
I'm replacing a silicon atom with an arsenic donor impurity.
I mean,
You're referring to like the crystalline
Change.
structure, right? How they make that diamond lattice. So you're removing some of them and replacing them with the donor, or just
Right. Now I'm replacing some of the silicon atoms in the diamond lattice with the donor.
well, I mean, the atom should be a different size, right? So it's
Right.
going to cause a change in the formation of the crystal structure somehow. I'm not sure
Exactly.
how it would, but I know it'd do it somehow.
Exactly. That's all that I was asking for. So if I replace a silicon atom with a foreign impurity, an arsenic donor impurity, that's a different type of atom. It's different from silicon, right? Therefore, it's a defect. It's an intentional defect that I've created because I need to introduce electrons in my transistor, right? But it's a defect nevertheless. The arsenic is a defect. So as far as the electron is concerned, when it's moving in the vicinity of the donor impurity, suppose the electron was traveling like this, the electron is negatively charged, it'll be attracted by this positive donor impurity, right? And it may deflect like this. Now, if I have more of these impurities, donor type impurities or acceptor type impurities per unit volume, do you think you'd have more or less of these collisional events?
more, because it would be varying from its periodic potential, right? Instead of it being constant, there's going to be more of those disruptions.
Exactly. Very good. And that's exactly what's shown over here. Okay, so excellent. So what I'm plotting over here are mobilities in different semiconductors, silicon, germanium, gallium arsenide, as a function of impurity concentration. And as I just pointed out correctly, as the doping goes up, the mobilities drop for electrons and holes. For low doping, the mobility saturates at a value which is limited by another scattering mechanism that I'll discuss next. That's the lattice vibrations or phonons. All right. Now let me ask you a few other questions. So this is mobility at room temperature, 300 Kelvin. Now I see that the mobility for electrons is higher than the mobility for holes in silicon. Any guesses as to what that might be? To understand that, you have to look at the expression for the mobility. So why do you think I have higher mobility for electrons than for holes in silicon? What could be the reason?
Change in the effective mass. Doesn't having the different atoms change its effective mass?
It's not different atoms. The electrons in the valence band have a different curvature. They have a gentler curvature. Therefore, the holes have a higher effective mass than the electrons. So the conduction band is.
Does the type of atom affect that at all, or is it just as long as there are atoms?
No, the type of atom affects that also. So that explains the second part. If you compare mobilities in silicon with germanium, germanium is a different type of atom. You'll see that the mobilities are different than in silicon. Okay, gallium arsenide. Now you have two different types of atoms in the zinc blende lattice, different mobilities also. Okay, so the type of atom matters. Whether I'm in the conduction or the valence band matters, because the curvatures depend on both the type of atom and whether I'm in the conduction or the valence band. Okay, and then the time between collisions also depends on the details of whether I'm looking at an electron or a hole. Okay. All right. So this information of mobility varying with doping also shows up in a plot of resistivity versus doping, shown over here on a log plot. Okay, how does that work? Well, rho we just saw is given by 1 over the conductivity sigma. Okay, and that's 1 over charge of the electron mobility times electron concentration per unit volume, which should be determined by the donor doping per unit volume, plus hole mobility times hole concentration per unit volume. Okay. Now, both of these terms would not generally be important. If I was looking at a p-type semiconductor, I only have to worry about this term, not about this term. Why do you think that is?
Which terms did you point to, sometimes it's hard to see.
Sorry. So if I was looking at a p-type semiconductor, I only have to worry about the second term, mu p times p, not the first term.
Thank
Any
you.
guesses? Why do you think that is? If I have p-type, which is the majority carrier,
Right, the majority carrier would be of the holes.
very good. So which number dominates, p or n?
Is it just because since it's log scale, it's large enough to ignore the other one, or?
No, let's not worry about the log scale over here.
Yeah,
I'm
I'm
just
just a bit
comparing.
confused on how it being a hole carrier or not actually makes one irrelevant largely.
Right. So if I have a p-type semiconductor, the holes are given by the acceptors, and then the electrons in the p-type are the minority carriers. Does anyone remember the expression for that? What's n times p correspond? What's n times p equal to? That was derived in the last class. It's given by Ni squared. So n in a p-type semiconductor will be given by Ni squared divided by p. Okay. So this is n subscript p. So if I have a p-type semiconductor, holes are the majority carriers, and I have very few minority carriers. So I can kind of ignore this term over here. Conversely, if I had a n-type semiconductor, the first term dominates over the second term. Okay. All right. So let's look at any particular type, say the p-type semiconductors there. Okay. So here now I temporarily ignore the first term, and I take the log of rho. Resistivity rho has dimensions of ohm centimeter. Log of rho becomes log of 1 over q mu p times p. Okay. Q, of course, is a constant. It's the whole charge. So I get minus log q mu p minus log p. So if I now plot log of rho as a function of log of p, the doping concentration, what should I expect? I should expect a straight line with a slope of -1. And that's indeed what I see. Okay, on a log plot, I get straight lines with a slope of -1. Okay. And there's a difference between the p and the hole and the n case, because hole mobility and electron mobilities are different. Electron mobilities typically are higher than hole mobilities, and therefore the electron resistivities are going to be slightly slower. If you look at very, very high dopings, notice that it deviates from this linear behavior. Any guesses as to why?
Can you repeat the first part of the question?
If I go to high doping levels, notice that the resistivity doesn't keep dropping linearly. It's slightly higher, right?
Correct.
The question, of course, is why. The answer is given in the previous slide. What happens at higher dopings?
There's more of the collisions that's going to affect the behavior differently.
Right. More collisions, mobility drops, right? So if mobility drops, that causes the resistivity to be slightly higher. It doesn't drop as minus log p or minus log n. Okay. So these curves are very useful. These are known as Irwin curves after the physicists who measure resistivity as a function of doping in semiconductors. So if you have a silicon wafer, there's electrical ways of measuring resistivity that I'll discuss hopefully at the end of the lecture today. And from that, you can infer what the doping is. All right. Once again, resistivities are different in different solids because we saw that the mobilities are different in different solids. All right. So the second very, very important scattering mechanism. So the first scattering mechanism is this ionized impurity scattering. It's very, very important because you always have to dope a semiconductor with donors or acceptors, depending on the device that I'm trying to make. So these are defects that I have to introduce intentionally, but unfortunate byproduct of that is you're also then creating defects which will cause scattering or collisions. Okay. Now there are also other possible types of defects, not due to donors. Those will also cause scattering, but those, at least in principle, you can avoid. You know, if you had perfect engineering, right? But the donor or impurity type defects, you have to put in, right? Because otherwise you don't get electrons and holes in the semiconductor. So it's kind of unavoidable in that sense. The second kind of defect that's kind of unavoidable is what is called phonon scattering due to lattice vibrations. Okay. Now here I'm showing these lattice atoms by these dots. black dots, and I'm showing them as being connected by springs. Okay. Of course, in a crystal, you don't have these tiny springs connecting them. These are nothing but these interatomic forces. Okay. Where do these interatomic forces come from? We discussed that in chapter 1 and beginning of chapter 3, where remember we plot the potential in a crystal as a function of separation between the atoms, and very far away you get the atomic levels, and then it goes down because of the bonding, and then it goes up because of the nuclear reaction. And we said that the atoms settle at a lattice constant corresponding to the potential minimum. Now near the minimum, it's kind of like a parabolic potential, and motion of a particle in a parabolic potential is simple harmonic oscillation. Hopefully you remember that from your freshman physics class. So these springs are basically modeling the simple harmonic vibrations about the equilibrium lattice constant. Okay. Now, once you postulate these springs, then you can imagine you have these atoms in planes which might vibrate like this. Now, if they vibrate like this, these springs will get squashed. Okay. And the restoring force will cause these atoms to bounce back, okay? And it basically will oscillate back and forth. Now, there are different vibrational modes. So for example, on the top figure, I can have a wave of these vibrations propagate to the right, and the corresponding displacement patterns of these atomic planes is shown over here, and these planes oscillate back and forth, okay? Where in this particular case, the atomic displacements are in the same direction as a wave propagation. These are known as longitudinal phonons, okay? On the other hand, the atoms themselves might vibrate in a direction perpendicular to the direction of the wave propagation. These are called transverse phonons, okay? Those are details also that you'll not be responsible for. All that I want you to understand is you can have atomic vibrations in a crystal, okay, about the equilibrium lattice sites. Now, if I heat up the crystal, would you expect these atoms to jiggle around more or less?
More.
Very good. That's exactly what happens, okay? Because when you heat it up, the atoms will have an average kinetic energy given by kT, where once again, this is K Boltzmann times temperature. So hotter the crystal, these atoms are going to vibrate around more and more and more, okay? And there's different modes of vibration. You have these longitudinal modes, transverse modes, and then these atoms can move, neighboring atoms can move in phase. These are known as the acoustic branch, or they can move in opposite phase. This is known as optical branch, okay? So they have different modes of vibration that you need not worry about. If you take a graduate course, you get into those details, okay? So for this class, just remember that you can have vibrations of these atoms and more violent vibrations at higher temperatures, okay? Now comes the key question. If these atoms are vibrating about their equilibrium location, and then these electron waves are propagating in this crystal, do these atomic vibrations lead to scattering potentials for the electrons, do you think? Remember, scattering is caused by any deviation from periodicity, right?
If they're shifting, like moving side to side, that's going to change the periodicity if they aren't doing it in like perfect sync or something.
Exactly. That's exactly what happens, okay? And that's what causes phonon scattering, okay? And as Ava just pointed out correctly, higher the temperature, more lattice vibrations, and therefore the mobility will drop due to lattice scattering, okay? Lower the temperature, less vibrations, less phonon or lattice scattering. But then for very, very low temperatures, you'll notice that the mobility is dropping again, and that's because of this impurity scattering that I discussed in the previous slides, right? As shown over here. Why is that? Well, as the temperature is dropped, the electron kinetic energies also scale as kT. So as temperature drops, the electrons are traveling more and more sluggishly, okay, due to thermal velocity. Now, which electron do you think would get deflected by this impurity atom more? Electron which is moving very fast at high temperatures, or electron which is moving slowly at a lower temperature?
Possibly the fast one, because if it's changing or the springs are moving at a different pace, maybe it kind of normalizes if it's going slower, possibly.
So the slower electron would be deflected more because then it's going to be in the vicinity of this charge longer. While if it's
Gotcha.
zipping past, it doesn't see the effect of that much, right? So that's responsible for this drop in mobility due to impurity scattering at lower temperatures. Okay, so lower temperatures, the electrons are more and more sluggish, and they can be impacted by these impurities more and more. Okay, while at very high temperatures, the mobility drops again because of more lattice vibration. So this is a characteristic behavior of mobility as a function of temperature. This is really the only thing that I want you to be responsible for in the exams. The rest of is details that I won't test you on. Now, the story gets more complicated and interesting at high electric fields. Okay, so far we are in the so-called ohmic regime, where if you plot the hole or electron velocities as a function of electric field, we saw that it varies, it's proportional to the electric field, and it's given by, say, mu p times E for holes, or mu n times E for the electrons, right? So if I double the electric field, the drift velocity doubles, and so on and so forth, okay? Under those conditions, then, we saw that V, let's look at holes, say, is given by mu p times electric field, okay? That's Ohm's law. If I take log of V, then, that would be log of mu p plus log of E. So now if I plot log of the velocity as a function of log of the electric field, I expect a straight line. What is the slope of the straight line going to be? On a linear plot, as shown on the top, what is the slope correspond to? If I plot velocity as a function of electric field, the slope is the mobility, mu p. But on a log-log plot, the slope is 1, right? Because if I take log of this, I get log of mu p. So the mobility determines the level at which these curves are, but the slope is now 1 on a log-log plot. On the other hand, on a linear plot, the slope is the mobility, right?
So mobility is
Yep.
velocity
proportional.
divided by electric.
Yes, it's a proportionality constant. Yeah, right. So that on a linear plot, it's velocity divided by the electric field gives you the slope, and that's the mobility. Okay, it's the same information plotted differently. On the top, I'm showing it on a linear plot, and the bottom figure it's on a log. That's all there is to it. Okay, but then you find that as you go to higher and higher fields, the velocity doesn't keep increasing linearly anymore, but it tends to saturate, and that's known as the saturation velocity. So what's going to happen? What's the reason behind that? The reason is, as the velocity increases at higher and higher fields, this drift velocity that's superposed on top of this random thermal velocity increases, and that increases the kinetic energy of the electrons or the holes. The electrons and the holes become hotter and hotter and hotter, okay? As they get hotter and hotter and hotter, they can bump more and more violently with these lattice atoms and cause them to vibrate more and more rapidly also. So what ends up happening is, in a semiconductor device, you hook it up to a battery, the electrons or the holes gain kinetic energy from this external battery, get hotter and hotter and hotter, but at some point they start bumping into these atoms more and more violently and start jiggling the atoms themselves. All right. So it's a two-step process. The external voltage first transfers kinetic energy to the electrons and holes, and as they collide with the atoms, they start the atoms vibrating also, and that's what you feel when you hold the backside of your laptop, for example. Okay, so your laptop microprocessor is, of course, powered by the battery. The electrons and the holes in your microprocessor chip are gaining kinetic energy from the battery. They're bumping into the atoms of the silicon crystal in your microprocessor chip. That causes the atoms in the chip to start vibrating. And that's what I feel as heat when I hold the microprocessor chip, or in this case, the backside of my laptop or or my cell phone or whatever when it's operating, okay? So when you touch a solid, it turns out you only get to sense the temperature, which is this random vibrations of the atoms themselves. You don't directly get to feel the temperature of the electrons or the holes. And that's a good thing, because it turns out the electrons and the holes actually heat up to enormously high temperatures. Okay, so you can typically heat up to maybe 10,000, 20,000 Kelvin, very, very high temperatures. Okay, while the semiconductor itself may heat up from room temperature, which is 300 Kelvin, to maybe 400 Kelvin, maybe 100 degrees C. Okay, sorry, 400 Kelvin. So that's like 70 degrees C or so. Okay. But the electrons or the holes are going to be at a much, much higher temperature. So hot electrons and hot holes go to much higher temperatures, while the crystal itself, the lattice temperature, is going to be a much lower temperature. And that's the temperature that I feel. Now, once I get such highly energetic hot electrons and holes, at some point, they start losing energy to this crystal and start heating up the crystal at the same rate as the electrons and holes are gaining energy from the external battery. And you reach a steady state. And when that happens, the electron velocity doesn't keep increasing any further. It saturates at what is known as a saturation velocity at some field, which is called your saturation electric field. Okay. Now that can be captured by a simple curve fitting type model like this. So velocity as a function of electric field now is equal to a low field velocity, mu times E, divided by this denominator. So you see that if mu times E is very, very large compared to the saturation velocity, which is this value over here, you can ignore the 1, and then the mu E cancels out, and you get V equal to V sat. Under those conditions then, so if I'm operating at a high field like this, above the saturation electric field, the current is no longer given by, so J for the electrons, we saw previously was given by Q N mu N times electric field, but now mu N times electric field has to be replaced by the saturation velocity. Okay, so you can expect problems of this type. Normally, I typically work out a few problems, but because we lost lectures, just look at these problems carefully, because in the midterm, you might expect problems along similar lines. Okay, so basically, if you give you a problem like this, depending on the voltage, you have to figure out whether I'm in the ohmic regime, in which case you use this expression, or if I'm in the saturation regime on the right-hand side, in which case you replace mu times E by the corresponding saturation velocity. Okay, and it could be that the electrons and holes actually saturate at different electric fields and different velocities. So that's a more complicated case, as in the worked out example. Now, gallium arsenide velocity field characteristics are very, very strange. Why do you think that's strange? What's funny about the gallium arsenide curve?
It goes up and then curves back down instead
Right.
of the others, which kind of just level out.
Right, that's very strange, right? Because normally you'd expect that as electric fields go up, the velocity should keep going up, right? And initially it does, but then you have a regime which is called negative differential resistance. All right. The reason for that is the band structure, and it's an effect known as a Gunn effect. Okay, so what happens is at low fields, the electrons do not have a lot of kinetic energy. They reside in this conduction band near k equal to 0, the so-called gamma point. Okay, but as it gains more and more kinetic energy, it can transfer to a satellite valley along the 111 direction, which is known as the L valley. Now, looking at the curvatures of these curves, which electrons do you think have a higher mass? Electrons in the L valley or the gamma valley? Actually, the answers are given right here.
Yeah, it'd be the ones in the less steep curve. Satellite Valley, I guess it is.
They'll have a higher mass, right? Higher mass has a, remember, mass is inversely proportional to the curvature, right?
Yeah. Has less of a curve. Well, I guess that's more of a curve. I'm not.
This is more curvy.
Yeah.
This is more curvy, and that's less curvy, right? So that has a higher mass than this. Okay. So what happens?
I've always thought of more curvy as like whatever is sharper for some reason.
Okay. Yeah. The sharper means more curvy. Okay. So initially the electrons have a lower mass, they're more agile, higher mobility, but then at a critical field, they transfer over and the electrons behave as if they're more massive are more sluggish, and therefore the mobility drops. And that's responsible for this so-called negative differential resistance. This is an effect first discovered by a physicist named Gunn, which is called the Gunn effect. And interestingly enough, this simple effect is the basis of a whole technology. We can make microwave oscillators in gallium arsenide based on this so-called transferred electron effect. Okay. Now, I'm not going to discuss this in this class. It's discussed at the very end of the book. If you're interested, you can flip through it. The point being, these subtle details about band structures can be the basis of very, very interesting effects in a semiconductor. Now, I was hoping to finish up the Hall effect. I'm not going to test you on that in the exam, but I think the homework problems that are due involve, one of them I think involves the Hall effect. I'll discuss this on Monday, but to solve the problems, and hopefully you can read ahead a little bit. So basically it has to do with the fact that in a semiconductor, you can now apply both electric field and a magnetic field. And if you have electric and magnetic fields, you may remember from physics, electrons are subject to what's called the Lorentz force, E plus V cross B. And because of this, if you drive a current in this direction and have a perpendicular magnetic field, you develop a voltage in the transverse direction, the so-called Hall voltage. And from that measurement and the measurement of the resistance, you can infer what the mobility and the carrier concentration in a semiconductor is. I'll discuss this in class on Monday. This will not be in the exam, but I think you'll need this in one of the homework problems. Okay, my apologies, I couldn't get to this. All right, any questions?
So in terms of the exam, I can't remember if you mentioned or not how it's currently set up. It was like set at like midnight, or it was like due sometime during the day, or will it be during class?
So it'll be during the class. Okay, so I'll make the exams available at around 8:45, and you'll have to turn them in by 10:30. Okay, I've set up the assignments on Canvas, so you'll turn them in just like the homework. Okay, so I'm going to post the exam a little bit ahead of the 9 o'clock start time so that we have time to print it out.
Yeah.
Hopefully all of you have printers at home. Yeah, and scanners. So you scan them and then upload them. Okay. Any other questions? All right, talk to you on Monday. So
Actually, one question really quick.
For the midterm, all that you're responsible for is stuff covered up to today. Yeah, go ahead.
For the homework due dates, I noticed that there is a bit of a difference between the ones like on the site and on the syllabus. I was wondering if those are going to be like adjusted for Canvas, or if they were just.
So right. So what I did was I uploaded a new course schedule where I moved down the due dates for I think homework 3 and 4. And I've also adjusted the times when you'll be able to see the solutions on Canvas. Okay.
Okay, yeah, I just know that like when it comes to like the to-do list, when it comes to the actual assignment due dates, the due dates for the Canvas thing don't line up with the
Oh, I see. So look at the course schedule due dates. Okay, so I guess I didn't change the due dates on Canvas. Sorry.
Okay, yeah, I think most of us knew that just from messages in the group text. I was just wondering if they were just gonna sit.
Right, and I'm trying to catch up. So I think week after spring break, I think we'll be pretty much caught up, and then we're back to the original schedule. My apologies. I'm rushing a little bit. I'm not going over the worked out examples, which I normally like to do, but having missed 3 lectures, it's a lot of catching up to do.
All right.
All right. Yeah.
And then, Professor, did you see my message real quick? I can't tell if you're still there.